for more than 30 years. And as a CTO is a Chief Technology Officer. He has been a leader of Hyundai Heavy Research Institute. Okay, do you have any question on schedule or any other things? Otherwise, we can go on to special guest lecture today. Professor Bob, please, go ahead, please.
부터 하면 될까요?
네.
예. Thank you, Professor Han. Hello, everybody. Good afternoon. Nice to meet you in class ME403 on Introduction to Naval Architecture and Ocean Engineering. I'm sorry, but we still have to use this video system due to the coronavirus. I hope everybody is healthy, well. My name is Jinsu Park. I had worked in the shipbuilding industry in Korea for 34 years and retired 3 years ago. Now I'm working on the research cooperation between KAIST and Hyundai Heavy Industry Group. My major was structural analysis and design. The ship is one of the main products I was engaged in. Today's special topic is hull strength of ship structures, the main body of the ship. I'm going to focus on the concept. I'll try to avoid the details. I was told by Professor Han in this class, most of you are not familiar with ships and shipbuilding industry, so I'll try my best to introduce the concept as simply and conceptually as possible. In general, when we are talking about design of some products, for example, ships, there are three main things that we are most concerned about. First, it's performance, like how fast ship goes, how large amount of cargo it carries. Second, it's safety. Is it strong enough during the lifetime? I mean, is it strong enough to endure the possibly the severest loading? Third, efficiency and economics. Does it have good value to make and maintain from a point of cost against the benefit? Generally, these three elements are considered together in the initial design stage and optimized to get optimum design solution. Today's topic, hull strength, is related with the second concept, safety of ship structures. Before we get into the subject, hull strength, I'd like to show you an interesting example of strength test of a small structure, a soda can. Which is probably very familiar.
Professor Park, could
Yes.
you share your screen, please?
Screen? Which one?
화면 공유, please.
화면 공유 안 돼 있어요 지금?
예. 안 돼 있다고요.
지금 화면이 어떻게 나와요?
그냥 얼굴만 보입니다.
희한하네.
화면 공유를 되어 있으면 화면 공유 해제를 먼저 하시고요. 화면 공유 버튼이 보이세요? 밑에?
안 보여요.
초록색 버튼이 안 보이세요?
예, 왜 화면 공유가 안 되지?
그러면 공유 해제 버튼은 보이세요? 빨간 버튼은 위에?
지금 아무것도 안 보이는데요.
그러면 줌 화면이 아닌 모양이네. 줌 화면이 어디 숨겨진 모양이네. 잠깐만, 제가 그걸로 할게요.
I'm sorry, but
이대로가 있어.
거기 지금 아까 이거 했는데 이거 하고 이거 공유를
근데 여기에 그 파워포인트.
예. 처음에 화면이 하나도 안 나왔어요?
하나도 안 났어요.
그러면 중간에 인터럽트.
나는 말을 먼저 하고서 하는.
이 페이지.
하십시오. 다시 하십시오.
오케이. I'm sorry, students. Can you hear me? And screen also?
Yes.
Yeah, thank you. And the first part, I just talked about the basic concept of general design concept, performance, safety, and efficiency. And next one is this one. Before we get into the subject, hull strengths, I'd like to show you an interesting example of strength test. A small structure, a soda can, which is probably very familiar with you. However, you may have never thought about its strength. How much weight can a soda can hold? It's an interesting question. Soda can generally is very thin, less than about 0.3 millimeter of aluminum to make it light. But also it's supposed to be strong enough to act as a kind of liquid container. In this slide, you see two load test situations. The left one is an opened and empty can. The can is vertically loaded and it collapsed under 55 kilogram force. The photo shows 48 at the moment, a little bit after the load reached the maximum of 55. On the other hand, in the right one, in the slide, the question is how much load a soda can hold in the unopened and liquid full condition. Actually, this unopened can undergoes many types of heavy loadings, like a large stack of soda can boxes on top of one another, as you know. Now let's see the test of
in
an
aluminum
opened one.
tank, like soda can or space rocket, it's going to be much stronger when there is some pressure inside. So I'm going to say that it's going to be at least twice as strong with the soda in it. So here we go.
Probably it looks like much stronger than the empty one. How much stronger? Can you guess? Twice, 3 times? Over 100? Over 200?
Whoa. Oh.
Yeah, over 300. Can you see the deformation ripples occurring in the cylinder part?
Oh, it's going to go!
Yeah, finally it ruptures. It's showing the deformed shape of the can, just right before it plates. Wow, how much load? It went
That
up.
was really nice.
Yeah.
And let's see the result. 360 kilograms, so way more. Yeah, that was really nice. And it failed like really slowly first before exploding.
Yeah, it went up to 360 kilograms, about 7 times stronger than the empty one, that one. I think this test shows what the concept of structural strength. You can maybe imagine how the thickness of the can has been determined based on the consideration of many kinds of ultimate loading. Likewise, ships' hull strength should be designed to resist maximum loadings by proper design of structures. As you know, the main target in this class is large commercial ships. In case of commercial ships, in general, how big load or what kind of loading can break the overall ship hull structure? In other words, what type of loadings should be considered for the hull structure to be strong enough and guarantee safety? When we are designing ships, ocean wave is the main external loading. So we usually think about how big wave can the ship withstand. Wave height and length that ships encounter during the voyage are very important and critical to the hull strength. What kind of external waves and internal cargo loading should be considered? These are the important subject in the design of ship structures. Ensuring safety in ship's lifetime, 20 years, is the main purpose of designing hull strength. Here are some typical examples of photos showing the entire loss of hull strength, probably as a result of undergoing excessive wave loading, big vertical buoyancy force at center part. These catastrophic structural damages rarely happen during operation at sea, but it happens when ship encounters more serious wave loading than the design wave, even though the probability is very low. Basically, ship is designed for the maximum wave loading of 10 to the -8 probability. That is the most serious wave loading among 100 million waves that ship is expected to encounter. Generally, the type of ships are classified according to the kind of cargo the ship carries. If it carries grain, ore, and coal, it's called a bulk carrier. If it carries oil, it's called tanker. Likewise, container carrier, gas carrier for LNG or LPG, car carrier, cruise and ferry that carries people and car, and warship for battle. The overall shape of the characteristics are similar, but the internal structures and functions may be quite different from each other, depending on the kind of cargoes. As you know, the largest shipbuilding yard is in Korea. About half of the total number of large commercial ships that was contracted this year so far are going to be built in this country, in Korea. I mean, in Hyundai, Samsung, and Daewoo. Next one. When we talk about ship, it may be defined in many ways. In particular, when we limit our concern to general commercial ship, it can be defined as a large watercraft that travels the oceans in sufficiently deep waterways. Also, it carries goods or passengers with specialized missions. By the way, hull refers to the main structural part along the whole ship length, usually made of steel or aluminum. Main loadings against the hull are waves and cargoes. So hull should be designed to be optimum in terms of low cost and sufficient strength, have the proper performance and hull strength. By the way, how big is general large cargo ship? Here is a good example showing how big it is. The largest container ship operating in the oceans currently is 400 meters long, about 60 meters wide. It is able to carry about 24,000 container boxes, which are 20 feet long containers. Big. More than 50% of the containers are loaded above the upper deck. This largest container ship was built in Korea, Daewoo, last year. Currently, bigger container ships are being designed in many shipbuilding yards worldwide. Next one. I'd like to talk more about hull. Hull may be said to be a watertight body of ship that is, main structural part, including cargo holds along the ship length. Hull is supposed to hold many kinds of cargoes, also withstand external and internal loadings. All part of the hull, so-called upper deck, may be partially open in order to manage cargoes. As structural complex, hull is composed of various elements such as plate, stiffeners, frames, bulkheads, etc. This figure shows the inside of typical foreparts of the hull or bulk area. It looks quite complicated and composed of many different types of structural members. However, as you see in this photo, the outside of the hull looks quite simple and smooth. Next one. This slide shows the typical mid part of hull structure in tankers. It is also composed of many kinds of structural elements, plating, longitudinals, stiffener. Most of them are welded to each other. I'm afraid most of you are not familiar with this terminology. In general, sectional shapes and arrangement are similar along the ship length. That is repeated at regular distance, 5 to 8 meters, in order to be effective in manufacturing. To make a whole ship, tens of these blocks are transported into a place you see in this photo and assembled together in the place of so-called. For your reference, here is a summary of shipbuilding process, which is roughly saying contract, design, construction, sea trial, and delivery. The whole process usually takes about 1.5 years. Among them, the construction process for a ship hull can be described as steel cutting, block fabrication, and block assembly at dock and ground, and then commissioning and outfitting at key wharf. This left side photo shows a big shipbuilding yard on the heavy industry, where you can notice bulk carrier and container ship are being assembled together in the same large dock. In the other dock, you can see 3 ships are being built in the same dock. I mean, the dock, the shipbuilding yard is very huge in general. At this point, I'd like to talk a little bit about basic concept of structural strength. Here is a photo. 2 persons are crossing a bridge. At first glance, I think the bridge looks quite dangerous. I wonder if it is safe or not. Is the bridge strong enough or weak? In order to answer these questions, in other words, in order to think about safety and strength of the bridge, we first need to, have to consider all of the loadings that can happen in the bridge's lifetime. Whether it's safe or not primarily depends on the loadings, such as weight of the persons crossing on the bridge, the number of people crossing together, their walking speed, wind force, direction, and the current state of the bridge condition. After all, the problem of strength and weakness is the problem of relation between structure and loading. Loadings are too severe and heavy, structures become not strong. It becomes weak. So designing structures eventually mean determining the size and thickness arrangement of the structural components based on the design loading for its lifetime. Here is the design concept of a hull structure. Basically, hull is designed to be structurally safe and functional in the lifetime of 20 years. Under maximum loading, wave loading, repeated wave loading, various kinds of cargo loadings, accidental loading such as slamming, impact, collision, etc. I'm going to talk about those loadings later in more details. Our structure should be designed properly so that cracks, buckling, and fracture do not occur during the lifetime. Usually, the largest wave loading condition happens under the sagging wave, like this top figure. Mid part of ship bends down and both ends go up. Repeated cyclic loading may continuously happen by encountering repeated small waves at ocean. The main external loading against the ship is wave loading, as I said before. In reality, there are so many kinds of waves that we meet when we sail at sea. From a design point of view, we assume that a ship encounters about 10 to the 8, 100 million waves in 20 years. We assume that some waves are regular. The shape of wave height and length is uniform, like this one. Some waves are irregular. The wave profile is not uniform. It changes all the time, like this figure. In terms of wavelength, there are so many different lengths of waves compared to ship. As you can see, some examples over here. Among these cases, the red color shaded situation where the wavelengths and is the same as the ship length, then the maximum, I mean the worst wave bending moment occurs. Besides, continuous cyclic loading is also applied by repeated irregular waves, sometimes causing to fatigue. Next, maximum bending moment. I'd like to add some more about bending moment, especially a case of bending moment becomes maximum. The total moment be divided into static and dynamic component. What is static? What is dynamic? The static is due to cargo load along the ship length, and dynamic load is due to wave load. In sagging condition, I mean the center part goes down and both ends go up in deflection. Maximum static moment happens when the center cargo hold is full and the other cargo holds empty, like this figure. Maximum dynamic moment happens, ship encounters a wave whose length is about the same as the ship. When the ship is laid on the wave like this figure, the two top position of wave is located at both ends. This is the case of our concern. The worst condition occurs, unfortunately, when these two maximum static, maximum dynamic conditions happen together. So this is one of the cases that designers are most concerned about when designing hull structures. Here are many photos showing possible situations that experience in rough sea waves. Basically, hulls are supposed to be designed to withstand wave loadings even in such a storm seas. Sometimes we can expect the wave loadings even expect ultimate loadings due to bar flare impact or bottom slamming, quite big wave height. Of course, most of the time during the voyage of ship, these states are not so severe, but we cannot evade the ultimate loading, but eventually we meet such a severe loadings. So we need to design hull against those loadings. Our designers always think it's the most critical condition. What kind of wave loading is most serious? Next topic is weak areas. In human, our body, which part do you think is the weakest? Of course, it varies a lot from person to person, but we may think that waist in our back is the part we feel many troubles, especially when we get old. Likewise, the mid part of the ship, in other words, upper deck, right here, and bottom plate, right here, midship in the middle of lengths are the weakest area in general. At midship, maximum bending moment is applied, inducing maximum stress, sometimes resulting in structural failure, such as cracks or the buckling. Cracks may be initiate and grow in time slowly, and finally become it comes fracture. Sometimes large stress may be induced plate beam to buckle locally. So I mean large deformation and the buckled shape becomes larger, so-called post, and reach final collapse. All design criteria should be such that cracks and buckling not occur during lifetime of the shape. For this purpose, hull designers determine thickness, arrangement of many structural elements. The figures in this right side shows hogging deformation of ship under a hogging wave, middle bent upward, stresses in upper deck, tensile, a very high tensile stress, and very high compressive stress at the bottom. These parts are very biggest area in ship structures. In ship structures, most common structural failure is cracks, as I told you, and may be defined a very narrow gap between two things, in this case, a separation of material in steel plates or beam, or frequently welded joint. Cracks may occur at weakest points and propagate across the deck, bottom, and any places at stress concentration areas such as bracket toes, welded connections, and so forth. Once a crack happens, generally it keeps growing into a long size because the ship keeps undergoing continuous wave loading voyage. In this photo, you can see an example of growth. It grew as long as about 20 meters, almost across upper deck. In this right side figure, there are some sketches showing typical locations of concentration points on the deck structure, where cracks usually initiate. Next one is buckling. Another type of most common ship structural failure is buckling. Buckling may be defined briefly as structural instability, as large lateral deformation occurring under compressive loading at plate panels and stiffness, or panel and stiffener together at the same time. A typical example of plate lateral buckling mode at compression is shown in this left bottom figure. In general, once buckling happens, post-buckling, that is, much additional bigger subsequent lateral deformation follows, sometimes causing the final whole ship collapse. For example, like this figure, under the hogging moment, in other words, the highest point of wave is at the center of ship, then the hull structure forms center up, bends down. This mode naturally induces the bottom structure experiencing compression. It may possibly cause buckling at the plate and stiffener in this bottom area. So you can see a simulation buckling mode. Stiffeners bent this way and that way. Plate deformed up and down, red and blue. It is interesting to see a bunch of adjacent plate undergoes buckling mode together. Sometimes the simulation, sometimes we carry out this kind of full-scale buckling test in order to confirm this simulation result. The purpose is to determine the adequate plate thickness and stiffness size, not buckling not to occur during the lifetime. In this slide, I'd like to talk about section of ship and the shape of section along the ship. Design of section is important because it determines the rigidity. Rigidity is sectional property closely related to the hull deformation, that is, deflection of the hull. It depends on the shape of section. Bigger rigidity is, the smaller deflection occurs. Here are some very simple examples of beam section A, B, C, D. The areas of sections are assumed to be the same. The shape of beam A is stronger comparatively against the vertical load, but it is weak to lateral bending, maybe weak to torsion. By the way, beam B is weak to vertical bending load. However, beam D is very effective for vertical and lateral bending, and also effective for torsional moment. It is so-called a closed section. So the basic concept when designing hull structures sections is to make it closed section as much as possible. If we need an opening on the deck in order to manage cargo, we should make the openings small as possible. This photo shows a typical block of a ship in a shipbuilding yard. It's a part of midship tanker. You can see a big closed section, and also you maybe see several small closed sections inside the big closed section. This kind of closed sections is very effective against hull girder wave loading applied in many different directions. Here are various sections of ship: oil tanker, two big closed section in a whole section, car carrier has many decks inside so that it carries as many cars as possible. Therefore, car carrier has a very big vertical and lateral rigidity in general. Sometimes maybe weak against the torsion in this case. Next, the bulk carrier, center cargo hold, and the two side ballast water tanks. So there are three closed sections. Next, container ship. Container ship has to have big opening on the deck, inevitably. In this case, the thickness of plates for the small closed sections around this blue part thickness should be increased enough to maintain the rigidity of the overall section of the required level. LNG carrier is similar with car carrier, having a big opening on the deck. So there are many kinds of sectional shape in ships. In this slide, I'm going to talk about basic knowledge of strengths of materials. Some of you may be not familiar with. In general, we use concept of stress and strain. Stress by sigma here, defined as force divided by area on which the force is acting. A strain, epsilon here, is defined as elongation divided by length. The relation between stress and strain can be expressed linearly or non-linearly using the constant of Young's modulus E, sigma equals E times epsilon. This graph shows the typical behavior of stress and strain for structural steel. If you apply force, stress begins going up linearly until it goes up to some limited level, yield stress. Beyond this limit, you cannot apply more force. Instead, elongation becomes large. Finally, it comes to fracture. Beyond yield stress, materials cannot resist more forces. So when designing some structures, we need to determine the thickness and size of the resulting to be less than yield stress. For example, 90% of yield stress. You continue apply force, elongation increase and become too large, it goes to a certain rupture. In this photo, right here, you see some standard specimens to test material strengths in this test machine in the lab. Let's see simulation of stress and strain of a specimen. If you apply force and increase it, stress goes up. Also, it deforms linearly in the first linear stage. If it reaches yield stress, it shows non-linear deformation. It keeps yielding, showing more increase of stress. Complicated structures, some hotspot local areas where stress is big comparatively. This kind of stress and strain behavior generally happens under various loading conditions. So finally, occur at this stress concentration. This one. Therefore, stress is regarded as the measure of internal resistance of the material to external load. And there are two kinds of stresses. Normal stress, as shown in this figure, is induced from normal elongation force. And stress, shear stress, results from twisting force. Likewise, strain is a measure of the deformation produced by the influence of stress. There are also normal and shear strains. All of the complicated structural deformation can be decomposed and expressed by these two types of normal and shear strains. Normal stress and strain are usually happening under tensile loading, positively and negatively. The direction is elongation and strain is the same as the direction of applied force. And by Hooke's law, the magnitude of stress is linearized with the material property constant, Young's modulus. As E, Young's modulus becomes bigger, it means it's hard to deform. Bigger force is needed to make the same elongation. Generally, Young's modulus of steel is about 3 times bigger than aluminum. So we use steel for structure undergoing large loading. Steel deforms 3 times less than aluminum and resists 3 times more than aluminum. At this point, I think we need to talk about beam theory, simple beam theory. In order to evaluate stress in a simple beam, a bending moment, because Hurst structure of ship can be regarded as a simple beam. In this theory, maximum bending stress in the middle of the ship is calculated by this equation. The stress sigma equals moment divided by I over Y. It's called the section modulus Z. I do not think that you need to know it well in detail. This equation means maximum bending stress in a beam is directly proportional to the maximum value of applied moment and inversely proportional to section modulus Z. This one, I just said you don't need to know it well, but just concept. So section modulus Z is a geometrical property determined by section. For example, in a rectangular section, this one, section modulus Z is B d square over 6. This is an example. But if you want to increase Z in order to decrease bending stress, we know it's more effective to make H bigger. You may know it intuitively. I think in reality, the section of hull of ship, this figure, is very complicated, as you see in this figure. So eventual purpose of hull design in the initial design stage is to optimize the arrangement plate and stiffness so complicated, but to determine the make it biggest section modulus, to make it the resulting stress less than the allowable limit, 90% of yield stress. That's the basic concept of designing hull section. Designing the section modulus of this complicated ship section. In actual design, stress should be lower than about 90% of yield stress to prevent failures can fracture. For this purpose, very tedious and complicated structural analysis are often carried out in office in the design stage. Sometimes stress should be much less than yield stress in order to prevent buckling and large deformation. For optimum design, many things are considered. For example, plate thickness, stiffness size, arrangement, cargo distribution, sailing route, considering wave loading and sea state, ship speed, etc. Yeah, that's a part of ship design. Here are some examples of structural failures that ships can experience in operation. Crack occurring at upper deck and growing to final fracture. Cracks occurring at upper deck and growing to final fracture. Cracks at packet toe of longitudinal stiffness below upper deck, and side shell probably initiate from, I think, internal structure. Sometimes you maybe see buckling outside the shell plate. From now on, I'm going to discuss loading situations against the ship. First of all, weight and buoyancy. As you all know, ship float on the water because weight, including hull, equipment, and cargo, is equal to buoyancy. Vertical equivalence is maintained. Therefore, if weight or buoyancy changes, ship comes to move to make another buoyancy change. Ship comes to move to make another equivalence. In actual buoys, wave height usually continuously changes. In other words, dynamic wave loading keeps applying to her structure. So ship inevitably continuously keeps moving. Here I summarize main design loadings. It's called the loadings. There are vertical and horizontal bending moment, torsional moment, the shear force. As impact loadings, there are half layer impact, bottom slamming, collision, explosion, impact. And there are various kinds of cargo loadings, and also vibration and temperature may act another kind of loadings. Now, here is a good video from YouTube of showing wave loading and ship response. So I want you to see it.
A simple understanding of the strength and forces acting on a ship's structure is also important. An optimal ship structure has the minimum amount of steel to provide the strength and stiffness necessary to withstand the full range of internal and external forces exerted on it, from sources such as the light ship weight, the weight of cargo, ballast, fuel, etc. And of course the harsh sea, marine environment, the movement of the ship and vibrations. The hull may be compared to a simple beam. When a force acts on the beam, it bends and stretches in accordance with the magnitude of the force and the strength of the beam. Loads generate vertical static forces in still water. Waves generate dynamic forces that act vertically, horizontally and transversely, also creating shear and bending forces, in addition to tension and compression. Longitudinal forces will be experienced in the bow due to ahead seas. So at sea, the ship's hull is continuously being exposed to a large number of forces coming from practically all directions. The same simple beam principle also occurs in complex combinations inside the ship's structure, where plating, frames, stiffening, girders, panels and brackets are built up from many separate small beam elements, all working together. Due to the many and variable forces acting upon them, these elements may partly fail and develop cracks and damage in critical areas, causing a serious reduction in local and overall strength. In addition, aggressive corrosion that is found when placing steel in the marine environment ruthlessly weakens the steel and its welded connection.
Yeah, I think it's very useful. First of all, vertical hull bending moment is the most important critical loading condition component. First, we think about static and dynamic, as I told you before. So we consider sagging moment or hogging moment. Okay, I'd like to skip. Next one. Next loading component is horizontal hull bending moment. First, I'd like you to see a video of ship motion simulation under side direction wave. A big regular wave is coming from the right side of the ship, and the ship begins to move into a rolling motion. Under this situation, generally horizontal, sometimes called lateral bending moment, is induced with large low rolling motion. Moreover, this horizontal moment is coupled with vertical bending moment. So stress at the upper deck corner maybe become seriously large. Sometimes, rarely though, suffer from loss of stability and final shows a large container ship undergoing big side rolling with side waves. Another important hull loading component is torsional moment. Torsional moment and its subsequent torsional deformation usually happen in oblique wave condition. In other words, in case that ship encounters a wave with 45 degrees against the course of ship. In this situation, water depths at the right side and left side differ. So this difference of the depths at both sides induces torsional moment continuously and cyclic. In general, torsional hull gather moment is very critical to energy, which have very large openings at that. So we know large opening is comparatively weak to deformation. You can see a simulation of structural analysis for typical hull deformation under torsion. It looks somewhat exaggerated. Next one is baffler. Another type of loading against the ship hull is impact loading. When a ship sails on the head sea, wave coming from the front, so with the wave direction almost zero, the impact loading may happen on the bar flare, the whole part of it. Bar flare is meant front structure above the water, this part. In this area, impact loading may cause permanent yielding deformation. You can see in this photo an example of yield deformation. For research of design, baffler impact pressures model test are sometimes carried out using pressure sensors installed at several points baffler. Next one. Another type of impact loading is bottom slamming. This loading case often happen for high-speed ship when the ship is sailing in head seas and moving vertically pitching motion, like as you see this simulation. When falling downward from the vertical motion, very high impact over the bottom, front bottom area. Sometimes it causes permanent yielding and fracture. Even though baffler impact and bottom slamming are local loading, it also induces another type of high frequency hull gather vibration. Next one, almost. One of loading conditions we need to consider when designing hull is collision, especially oil tanker and gas carriers, as LNG. We often hear about an accident to ship collision, as you see a case in this photo, where a large bulk carrier collided into smaller oil tanker. You can notice a big spillage of oil over the large area around the ship. So designers need to evaluate the strength of side structure over here against the possible collision force to see if the side structure is penetrated or not when it is collided by another ship. In general, it's very hard to test using a full-scale accuracy. So we usually carry out numerical simulation to evaluate side structure. This right side figure shows structural models of large oil tanker and LNG carrier used for simulation. Last one, another special type of loading is explosion. This case is very limited to warship. You may imagine many scenarios, explosion near or inside warship. Warship structural designers should understand the ship structural response to underwater explosion impact, because we need to carry out proper reinforcement to minimize casualties and damages, even though we cannot stop damages. For this purpose, real explosion test may be conducted but most of the cases are evaluated by using technology of FSI, fluid structure interaction. In this simulation, ship structure, large volume of water around the ship, explosive are included in the structure. Thank you. It's all. Yeah, thank you for your attention for a long time. I hope from you have more understanding of design concept of hull structures. Thank you. Yeah.
Thank you very much.
Yeah.
Any question to Professor Park? Because he has much experience in shipyard, you can ask other questions too. No.
This figure is icebreaker. Yeah. It goes usually out area to break ice meters thick.
Okay, then we can close the session today and then see you tomorrow, next week, Tuesday.
Thank you.
Thank you very much. Bye
Bye-bye.
now.
Yeah.